Good evening, sir.
Yeah, good evening.
Welcome to the FTP, sir. Now we are going to start the next session. Today we are privileged to have with us a distinguished academician and researcher whose contributions to these fields have been nothing short of extraordinary. We are delighted to introduce Professor Dr. ALOK Satpathy, Professor in the Department of Mechanical Engineering at National Institute of Technology, ROURKELA, Odisha. With an illustrious career spanning 31 years, Dr. Satpathy has been a pioneer in polymer composites, tribology, and plasma spray coatings. Dr. Satpathy's academic journey began with a degree in mechanical engineering in 1990, followed by an MTech in the thermal science from Birla Institute of Technology, Mesra. He has joined NIT Rourkela in 1993 as a lecturer and went on to earn his PhD in plasma sprayed ceramic coating in 2006. His research has been groundbreaking, and over the last decade, he has actively contributed to cutting edge advancements in his field. His research collaborations include esteemed institutions such as BARC Mumbai, IIMT Bhubaneswar, and CPET Bhubaneswar. His academic output is nothing short of prolific with over 300 research publications and 200 research papers at various conferences. As a dedicated mentor, Dr. Satpathy has successfully supervised 42 MTech students and 10 PhD scholars, with two more currently under his guidance. Some of his notable awards include SJ Memorial Award 2006 and the GM Memorial Best Research Paper Award by the Institute of Engineers India 2009. Beyond his significant endeavors, Dr. Satpathy is also a renowned author with three books of his series: Novel Coating Material, Focus for Microelectronic Applications, and Neural Fiber Composites. These showcase his expertise in advanced materials and their applications. Not only is he a leader in engineering, but he is also a certified Yoga teacher at the Prajapati Brahma Kumari Iswariya Vidyalaya. He actively conducts training sessions on mind meditation, stress management, self improvement, and personality development, in- integrating scientific knowledge with holistic well. We are truly privileged to have such an eminent scholar and mentor with us today. Without further delay, we join in welcoming Dr. Alok Satpathy.
Thank you, madam. Can you hear me?
Yes, sir. Yes, sir.
Can you see the slide?
Yes, sir.
Okay, good evening, everyone. Sorry for this technical glitch. And my topic today, I don't know, can you just make out something from the slides, no? Most of the, there is no writing. Most of the things are pictures only. So I think there won't be any problem.
Okay, sir.
I'm audible?
Yes, sir. Yes, sir. You are audible.
Okay. So thank you, IGIT Sarang, for giving me this opportunity to speak on a topic very close to my heart. As Madam has pointed out, I have been working on these areas for quite some time, for last maybe 20-25 years, particularly in the area of polymer composite and thermal spray coatings. And today, since the theme is manufacturing, so I would like to tell what engineering products can be developed using not conventional material, not high-end materials, not costly materials, but with waste material. So if we say waste, nowadays waste is also getting converted to wealth, provided the right kind of technology is adopted. So there are different types of wastes, like industrial wastes, construction wastes, municipal wastes, medical wastes, bio wastes, so agricultural wastes. So if we judiciously select the right technology, And if we select the right material for manufacturing the right kind of product, then the waste can be converted to wealth very economically and gainfully. My talk today will not be an in-depth talk about any waste to wealth conversion, but through this talk, I would like to generate in you certain inspiration or certain what do you say, drive, so that you can think of the wastes around you and try to convert them to some kind of valuable product by using proper engineering technique. In this context, we will be discussing about waste, industrial waste, bio waste, and construction waste. Now, uh, what are the different bio wastes and what we can do about it? And what are the different kind of industrial waste and what can we do about it? We can do many things, in fact, but today I'll be talking about two major engineering products. One is how can we use some of these wastes, or at least one of these wastes, to convert them to polymer composites for various engineering purposes, structural and technical components, and also how to convert these or how to use these industrial wastes for, or construction waste for, making thermal spray coatings. Now you can see in the picture a host of natural elements, very common and abundant natural elements. You can see cantala fiber, banana fiber, sisal fiber. Then you can see here the scale of fish. You can see the feather of a chicken or poultry feeders. You can see a coconut tree and coconut leaves. So all these are bioresources. So these are bioresources, and most of them are considered agricultural or biological wastes in our day-to-day life. All these things can be used, or most of these things can be used, provided we judiciously select the appropriate mode of technology and processes. Now, some notable construction and industry wastes are, these are the biological waste I showed you. Some notable construction and industry wastes are red mud. Red mud is a waste from this alumina refineries, copper slag, cement bypass dust, fly ash, LD sludge, blast furnace slag, granite dust. The list is in fact very long, and I am only giving a few number of wastes which are available in our surroundings, in different copper industries, steel industries, power plants, etc. Now, coming to one by one, red mud. Red mud is a aluminium plant, alumina plant waste. Alumina means it is first in the extraction of aluminium. The first step is conversion of bauxite to alumina, and in the smelter, then alumina is further dissociated to form aluminium metal. Now, our group has tried with this red mud as a potential filler in polymer composite, in epoxy, in polyester, and in some thermoplastic material like polypropylene. We have used red mud as a filler material and got some interesting result. So our purpose was to establish that red mud, in spite of being a waste, can be used for this purpose. Even in my own doctoral work also, we have tried to develop coatings out of red mud. No, red mud is waste, because normally in coating, the conventional coating materials are very costly. So by using an industrial waste, in fact, we reduce the cost of the raw material and carry on with that material and develop some kind of product which are comparable with a conventional product. Copper slag. Copper slag is another waste which is generated in copper industries, and the percentage of different constituents, and most of the constituents are metal oxides only. There's ceramics, iron oxide, silicon oxide, calcium oxide, and so on. So copper slag is generated in a copper plant, copper extraction plant, and copper slag has also been tried by many researchers, including us, for making polymer composites with different type of polymer matrices. Another common and very like, what do you say, widely abundantly available waste is fly ash. We are all conversant with the fly ash bricks. Most of the houses nowadays are constructed with fly ash bricks instead of red brick, and fly ash is the waste generated during the combustion of coal in the power generation process in thermal power plants. So in any thermal power plant, particularly in the eastern region of India, most of the power plants are coal-based power plants. So we have abundantly available fly ash, and they are dumped in the form of hillocks and hills around the, or in the form of pond in the vicinity of the power plant. And most of the fly ash are being used for making grip bricks, or a part of that is utilized for making cements. In spite of that, there are a lot of fly ash which are dumped as a waste. So researchers have been made to use these fly ash as particulate fillers in polymer composite, so that a value-added product can be made out of this waste. Fly ash again is a mixture of ceramic oxide ceramics, like mostly silica oxide and iron oxide, aluminum oxide. Then LD sludge. LD sludge is, in steel plants, the iron to steel conversion takes place in LD furnaces, and in the process of steel making, there is a sludge or a waste developed that is called LD sludge. LD sludge basically contains iron oxide, calcium oxide, silicon oxide, and so on. And this waste is simply dumped in the steel plant site. I come from a steel city, and we see here there is a huge deposit of, or you can say dumping of LD sludge and blast furnace slag all around the steel plant, and their utilization potential is very low. It is hardly being utilized except for pit filling and this road making. So we made an attempt to convert these to, use them into polymer composites, where conventional filler materials are replaced with this waste. And in the process, what happens? We are successful in reducing the cost of the composite. Coming to the construction waste, what are different construction waste? So far, the waste that we are discussing are industry wastes. Now, if you consider construction waste, the major construction wastes are marble dust and granite dust, because most of the high-end houses these days are made up of, marble. The floorings are made up of marble or granite, and in the marble processing units and granite processing units, cutting units, there is huge amount of granite dust and marble dust generated, and which creates health hazards, which are not used anyway in any other purpose, but they are instead, on the contrary, they are causing health hazards in the vicinity. People who inhale them through their while breathing suffer from various diseases. So granite dust and marble dust are considered nowadays as potential material for making different engineering products. One such engineering product that we will be discussing here for marble dust is polymer composite, and another is the high velocity oxyfuel spray coatings made up of marble dust. So basically we will be focusing on these two products, polymer composites in general and thermal spray coatings. Now, what are these things? Now, what is a coating basically? Coating is a layer of material which is formed naturally or synthetically or deposited artificially on the surface of any object to made up of another material. For example, you have a stainless steel substrate, and you want to coat it with a very high or hard material. So you can coat it with aluminum nitride or silicon carbide. Then what happens? The surface becomes very hard, whereas the core is the stainless steel or mild steel. So this helps the material or engineering component to withstand the environmental attacks which are likely to be on it in the process of operation at the workplace. For example, if you say coat, suppose there are two mild steel machine parts which are in relative motion with each other. So there will be friction, wear and tear, and after some time what will happen? They wear out from the surface, and there will be noise, there will be mismatch in the dimension, there will be more energy loss, there will be unnecessary heat generation, all those problems will come. But if you coat them, if you make a coating out of some harder material, say for example titanium nitride, if you coat it with titanium nitride, then what happens? The surface of both the members becomes very strong, very hard. When they become very hard, then in spite of repeated sliding, the wear and tear, the rate of wear and tear will become drastically reduced. So the life of the plant will improve, and the other side effects also will be mitigated. Like for example, the unnecessary heat generation or noise actuations, all those things will be reduced. So basically the coatings are helpful because that solves the component degradation problems, it helps in material saving, and it helps in enhancing the efficiency of the entire system. So this is one thermal spray coating. What is the use of thermal spray coating? What is a composite? Because we will be discussing two uses of this industrial waste. One is coating, one is composite. What is a composite? Composite is little different from alloy and solution and mixtures. Composite is a material made up of two or more constituent materials. There can be two, there can be more than two, which which they have significantly different physical and chemical properties. And when combined, they produce a material with characteristics different from individual. Now, you are mixing two materials, but uh, they do not lose their chemical and physical identity. They remain together, form a rigid structure, and we call it composite. One basic condition in making composite is that one of the constituents should not get dissolved in the other constituents. So, and depending on again, I mean, what is mixed with what? Like for example, you are mixing glass fiber in epoxy, then glass fiber is the reinforcement and epoxy is the matrix material. Similarly, if you have a ceramic material as the matrix, then you can call it ceramic matrix composite. If you have a polymer as the matrix material, you call it polymer matrix composite. And similar, in the similar manner, if you have a metal as the matrix material, then you can call it metal matrix composite. So ceramic matrix composite, metal matrix composite, and polymer matrix composite. There are different composites. So similarly, in case of reinforcement, the reinforcement can also be fiber reinforced composites. There can be polymer reinforced composite. Particulate reinforced composite. There can be flake reinforced composite, depending on what you have. So polymer composite basically can be determined or can be analyzed based on the matrix material. Matrix material is the main binder material. The base material on which the composite is fabricated is called the matrix material. In case of a glass fiber epoxy composite, epoxy is the matrix material. In case of a aluminum silicon carbide composite, aluminum is the matrix material, metallic matrix. Silicon carbide is the reinforcement. Similarly, fibers. Fibers, you can have bidirectional fiber, you can have unidirectional fiber, you can have synthetic fibers like glass fiber, you can have natural fibers. In the first slide, I show you a lot of fibers like banana fiber and coconut leaves, coconut coir. So those are natural fibers. Fibers can be natural, fibers can be synthetic. Fibers can be long, fiber can be chopped or short fiber. Fiber can be in the form of unidirectional threads, or it can be in the form of mats. Short fibers can be aligned fibers, or they can be randomly oriented fibers. So there are various classifications again in the fiber category. Now, if you do not use fibers, then also you can make composite by using particulates. Particulates are particles, powder form, dust. The particulates can be reinforced in matrix material and composites can be formed. Of course, the properties of fiber reinforced composite, particulate reinforced composite, composites with different matrices, composite with different fibers, composite with different types of particulates, with different content of particulates, decide what the properties of the composite will be. Now, as we discussed, matrices are the main binder in a composite material. So matrix again can be, in case of polymer matrix, I am telling, I told you in the beginning that matrix can be metallic, ceramic, or polymeric. Depending on the composites are called PMC, CMC, or MMC. But again, if you come to polymer, again the matrices can be different. The matrices can be like thermoset matrix or thermoplastic matrix. For example, epoxy, polyester, then vinyl ester, phenolic resin, these are all coming under the thermoset category. And nylon, polypropylene, polyether ketone, polyether ketone, these are the these are the these are the matrices which are coming under the thermoplastics. Coming to fibers, the broad classifications are depending on the, I mean, if you in regard to the type of fiber, either the fibers are synthesized, man-made, artificial, or they are natural. Natural means the fibers are extracted from natural resources. For example, coconut leaf fiber, or for example, coconut coir fiber, or jute fiber, or bamboo fibers. These are the fibers extracted from plant resources. So they are called natural fibers, and often they are also called green fibers. And the composites that we make out of the green fibers are called green composites or natural fiber composites. Of course, out of that asbestos is a mineral, it is available naturally, but it is not a green fiber. It is called a natural fiber, but it is a natural mineral fiber. Whereas all other plant-based uh, fibers are called green fibers. Similarly, fibers can not only be derived from plant, they can be derived from um, animals and birds also. Depending on which part of the plant or animal you are using as fiber. The synthetic fibers are synthesized. They are um, manufactured. Examples are most widely used synthetic fiber is the glass fiber, and they are relatively stronger. That tensile strength is much higher than natural fibers, not comparable. And you have carbon fiber, which is the the strongest known fiber so far. Then Kevlar fiber, aramid fiber. So these are the other various natural fibers. Now, natural fiber, as I told you, they can be resourced from animals or from mineral resources or from plants. And what are the fibers that are extracted from animal sources are, like for them, the horsehair. Then from bird species you can extract this feathers of birds. It's a very interesting fiber, and very less work has been done. Those who are interested in this audience, if anybody is uh, trying to do any work on natural fiber, then the most promising area is now feather based fibers. We have done some work with poultry feather, that is the chicken feather, but other feathers can also be tried, and they are giving very wonderful results. Then coming to particulate filled polymer composites, the nature of these composites is slightly different. They are slightly, like in construction, they are slightly configuration, they are slightly different from fiber reinforced composites. In the fiber reinforced composites, small or long fibers are reinforced within the matrix body. But in case of particulate filled polymer composites, in place of fibers, you have powders, small particles. Depending on how small the particle is, you can call them macro particulate composites, then microparticulate composites, or nanoparticulate composites. If they are so small that their dimension is in the order of nano, then in that case we can call them nanoparticulate composites. So particulate filled composites have their own advantages and disadvantages. The advantages are many. First of all, if you use particulates in place of fibers, then they are basically done to improve the mechanical properties like hardness, impact strength, and compressive strength. Suppose you are using a harder material. Say, for example, I am taking the same example. If you are taking silicon carbide in epoxy, then the hardness of epoxy composite will improve drastically, because silicon carbide is hard and epoxy's hardness is very low. So you are incorporating some hard material, and obviously the hardness of the bulk hardness of the composite will increase. So also the impact strength and compressive strength. Sometimes You want the composite to be thermally insulative or thermally conductive, or electrically insulative or electrically conductive. Accordingly, the right kind of particulates is to be incorporated in the uh, matrix, so that you get the right resulting properties. Suppose you want some polymer composite to show lower coefficient of thermal expansion, then you have to select such particulate who has intrinsic lower CTE, lower coefficient of thermal expansion, thermal expansion coefficient. Or sometimes particulates improve the glass transition temperature of the polymer. So there are various reasons why the particulate composites are found to be in use in polymers, so that because of this enhancement of these properties. But one thing is that when you are incorporating fiber, the strength improves, tensile strength, because fibers take a lot of they share a lot of the major portion of the applied strength load with them, which the particulates cannot do. Now, with particulates, you can make the composite harder, so they improve in tribological properties, improve in optical and electrical properties, and of course, reduction in cost. Reduction in cost is very relevant to today's topic. Today's topic, we are discussing industry waste and construction waste, and these wastes are of low cost, isn't it? The theoretically the cost is zero. Suppose there is a industry where the red mud is dumped, you are bringing truckloads of red mud, then they will not charge any price. It is theoretically of zero cost. So when you are making composite out of them, naturally the cost of the composite as a whole will reduce. Then ease in processing. For fiber reinforced composite, you have to make some specific routes and processes, but incorporation of particulates into polymer is comparatively very easy, and the processing is very simple. You don't require any high-end or intricate machines to make the composites. One more important thing is that with particulate filled composites, you get a product which is more isotropic in nature. Isotropic means we know that the the product will exhibit same properties in all directions. The properties do not differ from direction to direction. I mean, along all the direction, it will have the same properties. So all the composites that are available are anisotropic in nature, but when you are making particulate field composite, they are relatively less anisotropic, or we can say they are more isotropic in nature compared to fiber reinforced composites. Now, what are these particulates? Which particulates are being used? Conventionally, I mean, in the world of polymer composite, if you have to go for particulate field composites, then the conventional fillers are oxide ceramics, nitride ceramics, carbide ceramics like silicon carbide, titanium nitride, aluminum nitride, boron nitride, then aluminum oxide, iron oxide, then silicon oxide, chromia or chromium oxide, yttrium oxide. So these are the conventional fillers. Conventional means they have specific properties, and these properties are, I mean, the benefits of these properties are taken by incorporating these fillers into the polymer. Now, all these fillers that I have listed out are all expensive. They are costly because they are synthesized and they are purchased from the market, and they will have uniform size and shape, and they're costly. But if you are able to replace them with industry waste, then what is happening? The filler cost is drastically reduced, which is actually reducing the overall composite cost. So by replacing the conventional fillers, you see, for example, if you make a polymer composite with 30% boron nitride or 25% boron nitride in it, suppose you make a composite epoxy and hexagonal boron nitride, and we have made this particular composite we have made for electronic applications. Now if you do this, then what will happen? Whatever will be the cost of the composite, if you replace this boron nitride by some conventional or non-conventional filler, that means waste filler, then what will happen? The cost will drastically reduce, because in a boron nitride epoxy composites, the 60% of the total cost of the composite goes to the cost of the particulates or the filler. Okay, there is no fiber here, only filler. So that can be saved by using a construction waste or a industrial waste, provided that construction waste or industrial waste is also giving comparable properties. Not that everything has to be replaced. Anyway, we will discuss polymer compost using construction industry waste, and let me tell out what is the research scope and applications. I have listed out some construction waste such as granite dust and marble dust. These dusts are wastes because they are generated at the time of marble cutting in the cutting processing units or granite cutting, and these wastes are not used at all. They are dumped in the site, they are just thrown down the drain, and they cause human health hazards. Similarly, industry waste, most of the industry wastes are dumped in the plant site, and they uh, they not only pollute the land, they pollute the environment. And even though they are used for various purposes, the utilization potential of many industrial waste in India and throughout the globe is small in the sense only maybe for example, fly ash is very widely used, but still then utilization potential of fly ash is 60 to 70%. So that means 30% of fly ash generated throughout the globe is still lying unused. And forget about blast furnace slag and LD slag and all, their utilization potential is still lower. So what I am trying to impress upon you is that not to show our knowledge or our work to you, but to impress upon you that there is a large research scope and scope, promising scope in this area, where you can select the waste and try to use them in some engineering processes to make a valuable product. Here I am discussing only two things. One is coating and one is making polymer composites. But there can be several other options which can be explored. That is what it is my purpose of sharing my ideas with you. Now, there is a small case study. I am just sharing some of our results of mechanical and dry sliding wear behavior of waste marble dust filled polyester composites. So we made some polyester composites out of with using marble dust as the filler material, and got some very promising results. The marble dust were procured from Rajasthan, and the polyester is procured from local market. Polyester is a thermoset polymer, and as I told you, epoxy, polyester, vinyl ester, and phenolic resin, these are coming under the thermoset polymer category. The thermoset polymer, why you have chosen thermoset polymer? Because for making composites from thermoset polymer, you don't require any high-end machines, whereas you don't require a compression molding machine or injection molding machine. But in case of a, if you want to make it with a thermoplastics like polypropylene or nylon or polyether ketone, then in that case you have to go for high-end machines like compression molding machine or injection molding machine. All right. So we are discussing here the mechanical properties that we obtain and the dry sliding wear behavior of waste marble dust filled polyester composite. Now this is a picture of the polyester, unsaturated polyester resin which is available in the market, and this is marble dust. Marble dust, as I told you, is generated in the marble cutting industries, and these marble dust are sieved to like to obtain micro-sized particles, 58 micron, 90 micron, 105 micron, like that. So three different size ranges of marble dust we obtained, and then we made the composite by uh, a process called hand layout technique or solution casting technique. Solution casting technique, if you have a beaker where you put the polyester which is liquid, and then put the marble dust and stir it, and then you add the right amount of right proportion of the cobalt acetate, which is the accelerator and hardener, then after 24 hours it gets within 24 hours it gets hardened up and gives you the composite. Okay, this is one. Another thing is that you can also hybridize it. Hybridization means, because as I told you, the particulate composites cannot give you strength, so you have to hybridize it with a fiber. Now what we did, we took epoxy glass, sorry, polyester glass fiber composite. In the polyester glass fiber composite itself, we incorporated marble dust. So we got a very, not only hard composite, we also got a strong composite. That means it is capable of withstanding or taking, sharing the axial pull load, axial load, along with the impact load. That's the beauty of hybridization. Hybridization means simple. Hybridization means simply incorporating two reinforcing element instead of one. In a pure particulate field composites, you are incorporating only particulate in epoxy. In a pure fiber reinforced composite, you are incorporating a fiber into epoxy, nothing else. But in a hybrid composite, you are reinforcing fiber along with a particulate or a dust material with the polymer. Now these are the samples, and the samples of different size and shape as per ASTM standard are to be prepared, because they are to be subjected to various tests, and when they are subjected to various tests, we come up with different results. So these are for compressive, some of the samples are for compression test, some of the samples are for tensile test or wear test. Our target was to develop a wear resistant composite out of marble dust, because marble dust is supposed to be hard material, and if you incorporate marble dust into polyester, which is a softer material, we expect that the hardness of the material will, of the composite, overall hardness of the composite will increase. So we have incorporated marble dust with a purpose. The purpose is that it might help in getting higher hardness, so that it can be used for tribological purpose. What is tribological purpose? It is a tribological applications. Tribological applications means application where the friction and wear play a very important role. That means the material degrades because of repeated friction and wear, and if we can replace the conventional material by a hard material, then perhaps the life would increase. That was the purpose. So in the physical properties, once you make a composite, this is for I'm telling it for the people who are interested in working with composite. You select a raw material, the matrix and the particulate and the fiber, make a hybrid composite. Once you make a hybrid composite, the composite is to be evaluated in terms of its properties. So the basic few properties are to be evaluated, like for physical properties are like for its density, because composites are supposed to be lightweight materials. Lightweight materials means their density is to be less than metallic composites. So density measurement is very essential. Density measurement also gives us another information, that in the process of making the composite, there may exist or there may get created certain voids and fractions, voids or what do you say, empty spaces in between because of the entrapped gas and air. So that might affect the strength of the composite. So by incorporating or by measuring the density practically and by calculating the theoretical density theoretically, the difference can be taken as the presence of voids. So we can find out what is the volume fraction of voids present in a particular composite, and more is the volume fraction, less will be the strength. So care is always to be taken to reduce the volume fraction of voids in any composite. So these are the data. I'm not reading out the data, but you can see that as the volume, as the filler content, as the marble dust percentage is increased, then the voids also are increasing. That is the reason, because sometimes what happens, our steering is not proper. Sometimes there is improper weighting. There is some irregular corners, sharp edged corners of the particles which are not getting weighted, fully weighted by the liquid polymer, and so on. There are various regions which needs further investigation. Now, once the physical characterization is done, microstructural characterization is very pertinent to do, because microstructural characterization gives us an insight to what is happening uh, within the composite. Okay, so we can go for scanning electron microscopy. The first left side, you can see the scanning electron micrograph of or marble dust. It is clearly showing the, tentatively showing the size and shape of the marble dust which are naturally found. And then the right side, you can see electron microscopy of the composite. So you can see that the marble dust has mingled with the, mingled means not getting dissolved, but it is spread across the matrix body. And the diagram below are the EDX mapping showing the elemental features. What are the elements present in the raw material, that is the filler, and the composite. It is basically calcium, silicon, magnesium, oxygen, and carbon. Now, because we are interested in improving the hardness of the material, so it is again pertinent to find out the phases, identify the phases which are present in the composite, and to identify the phases, different phases present, because marble dust is not a uniform material. Marble dust is a mixture of various oxides. So various oxides, again, they are in various phases. In the composite, in during the process of composite formation, these marble dust are spread across the composite, and therefore when we make a XRD, then we know what are the different phases present. And we see that in the composite the different phases are calcite, hematite, silica, and quartz. And individually all these phases are hard phases, and that makes the composite a harder composite compared to the hardness of individual constituents. Individual constituents means individual constituents are polyester and marble dust. It is harder than the polyester. Now, X-ray diffraction is a must after the density measurement. Then, although we say that composite is a combination of two material, one matrix and one reinforcement, but not that any material can be mixed with any material to form a composite. The pair has to be judiciously decided, and there must be some kind of somewhere some kind of uh, bonding mechanism, so that the composite fabrication is long lasting. Otherwise, the if the bonds are loose, then in that case what will happen, the composite, it will only be a mixture, it cannot be a rigid structure of different constituents. So for that, the chemical analysis is done. Chemical analysis means an insight to the chemistry of the different constituents is required, which is carried out by Fourier transform infrared spectroscopy. This FTIR spectroscopy is not the cup of tea for mechanical engineers, but it is done. It is to be done in a chemistry lab or a material science lab to find out what are the different functional groups present in the constituent materials, so that the chemistry of bond formation can be ascertained. What is important to us, the mechanical engineers, is the mechanical characterization of the composite. After the physical density measurement and microstructural characterization, mechanical characterization is a must for any composite we make. In the mechanical category, we have to find out what is the uh, tensile strength of the composite, what is the compressive strength, what is the impact strength, and if it is a laminated composite, what is the interlaminar shear strength. So it is very important, because the strength property evaluation is a very important part of composite characterization. Unless you know the strength, how can we use it for a particular purpose? So we must know different strength values, such as tensile, compressive, impact, and interlaminar. So all these things are to be evaluated. There are specified ASTM standards, American Society for Testing of Materials. There are ASTM standards. The specimens are to be made H per ASTM, the respective ASTM, and there are standard machines like universal testing machine and this impact tester for finding out the values of these composites. Now these composites, it is also important to know the compressive strength, because the tensile strength and compressive strength will vary. If the fibers are, if the fiber content is more, it is expected that it will be very strong in tension. If the particulates are harder, then it is expected that the compressive strength will be more. But that is to be ascertained. How much more or how much less is to be ascertained by proper evaluation of this. Now, impact test, because in the workplace, the composite, wherever it will be used in the engineering workplace, it is very likely that they may experience some kind of impact sometime during the operational tenure. So, impact strength of the composite may lead to, I mean, the lower impact strength of the composite may lead to failure of the material. Therefore, the impact strength is to be ascertained by properly designed impact test, and the izoid impact tester is normally used for this. So here is a chart which is giving you the different property values for marble dust filled polyester composite. Here in this particular work, my group has taken three different, I mean, marble dust, same marble dust, but of three different size ranges: 58 micron, 110 micron, and 155 micron. Three different size. That's the average particle size. It is done with a purpose to find out whether the particle size has an impact on the properties or not. And we found that it has. So if you make lower, I mean, the particle size is less, then we found that the strength is also less. The particle size is more, the strength is more. Okay, so there are specific reasons for that which needs special kind of investigation. Same also in case of the tensile strength, flexible strength, impact strength, and their modules. So because the size and shape has a very prominent role to impact the strength property values. Now these are the variation of the different strength properties in terms of a graphical chart. So you can see that the composite with 55 micron particulates, 110 micron particulates, 155 micron particulates are different. The properties are different, although they are appearing same to a certain distance. After say filler content of more than 16%, they are differing. So depending on what flexible strength you need for a particular application, depending on what tensile strength you need or what modulus you need, accordingly you can tailor make the composite. From this graph will help us in finding out a particular composite which is required to exhibit a particular amount of tensile strength. For example, we want a composite which must exhibit a tensile strength of 60 megapascal. So we will take 8% of filler content, and we'll take either 55 micron or 150 micron depending on the availability of the particulate filler. Excuse me. Similarly, the hardness can be measured either Pickers hardness, Sordi hardness, or Brinell hardness depending on the availability of the instrument. So you can see that the hardness also gets affected, though marginally, with the size of the particle. Okay, now that is why the size of the particle, shape of the particle, content of particle, how much content, 8%, 16%, 24%, that is to be decided very precisely and judiciously depending on, of course, the requirement. Is nothing that, I mean, not that 24% is good and 80% is bad, not like that. I mean, what is our requirement? First we have to see. Once we see the requirement, accordingly we can design, the material design can be done. Then for this particular marble dust reinforced composite, our target, as I told in the beginning, was to find out its dry sliding wear characteristics. So dry sliding wear characteristics are to be evaluated by a sliding wear test. In this context, let me very briefly tell what is wear. Wear, we know, wear is a word very common to mechanical engineers. It is a progressive loss of material from the surface of any component that is called wear, and it happens due to the relative motion between two surfaces. Or in a still more common term, we can say the loss arising out of friction. Okay, and to the industry, this friction losses or the wear losses is a very high cost element. Basically, there are three wear modes: adhesion, abrasion, and erosion. There are other wear modes as well, but broadly we can categorize them as adhesion, abrasion, and erosion. Dry sliding wear is a adhesion wear mode, and the dry sliding wear properties can be of the composites can be evaluated by a pin on disc wear testing apparatus, where a disc will be rotating and the pin is made out of the composite material, is to be made in contact with the rotating disc, and time to time the wear loss or the mass loss or volume loss due to wear is to be measured. And here there are different players again which affect the what do you call the wear rate, and they are the sliding speed, sliding distance, normal load, filler content, etc. Now once you take the readings at different levels of sliding speed, sliding distance, normal load, and filler content, we can find out the wear rate. The wear rate is basically expressed as specific wear rate, whose units is millimeter cube per Newton meter, where Newton is the normal applied load, and meter is the unit for the sliding distance. Now then the specific wear rate are calculated, and even if you take it for a small number of experiments by using neural network, you can generate more data for specific wear rate for a range of input variables within and beyond the experimental domain. For example, sliding velocity in the experiment, if you are taking 25 to 100 meter per second, then by using an artificial neural network, you can predict the wear rate for say 25 to 300 meter per second speeds. You can expand it. It is kind of extrapolation, but extrapolation with a logic. Now these are the different sliding wear test results. So how the sliding wear is varying, and in the right side you can see this is the what you say, this is the mean effects plot. Mean effects plot tells that out of the many player, the sliding distance, sliding velocity, normal load, and filler content, which is more important, which is the most important, or which is the most significant player which affects the specific wear rate. Now which is the which is the most significant player? Now you can see that the D is the filler content. Filler content is like 8%, 16%, 24%, and 32%. These are the different filler contents we have taken at the first place, and we found that the slope of this curve is highest, and therefore this is considered to be the most significant factor which affects the specific wear rate. So wear rate is affected by filler content. That is the conclusion. So coming back to the overall analysis, we can say, therefore, since the particulate filler is the most important factor affecting the wear rate, so if you can select the particulate filler in a right and judicious manner, then your composite will be a perfect composite, to combat the friction and wear. Now these are some of the data where the artificial neural network is used for simulation purpose. You can simulate it. ANN predicted specific wear rate for different sliding velocity and for different filler content. This is for different filler content at different sliding velocities. So such simulations can be obtained. Now, if you come to the morphology of worn surfaces, under the scanning electron microscope, if you see that what are the basic damage mechanisms, they are you can see the wear tracks here and wear tracks on the micrographs. You can see debris formation, then fiber fracture, fiber fragmentation, the particulate breaking, and particulate fragmentation. These are the plastic deformation. These are the prominent mechanisms which results in the formation of, or you can say, results in the mass loss due to wear in a particular workplace. So once you have an insight to the damage mechanism, it becomes easier for the engineer to rightly design the material. So in the first part, we can conclude that industrial waste, construction waste can be used for making polymer composites, and they can be gainfully used. They not only reduce the cost, they also uh, improve the functional properties, and the ease of processing also is used, and they also make a secondary benefit, that is the disposal of the industrial waste. Very briefly, I am touching the second part. The second part is thermal spray coatings. Like we can use waste material or construction waste material for thermal spray for polymer composites, we can also use for thermal spray coatings. Now, thermal spray coatings are widely used in industries, and there is hardly any engineering surface which is not coated, because surface treatment has to be done on every engineering component, and coating is one of the most widely used surface coating technique, surface modification technique. But thing is that the conventional coating materials, which are again zirconia or silicon carbide or aluminum nitride, titanium nitride, borides, and some oxides, they are all very costly. They are spray grade powders, and these spray grade powders are very costly. And in a coating activity, in a spraying activity or surface modification activity, 65% or 50 to 65% cost goes to the cost of the spray grade powders. This particular thing fascinated researchers like us to explore the potential, the coating potential of certain industry waste such as red mud, copper slag, CBPD, fly ash, blast furnace slag, granite dust, etc. So these are the list of waste materials, but all these waste materials have not been coated so far. So there is still room for, like for example, to best of my knowledge, copper slag has not yet been coated. Then then blast furnace slag is not yet coated. Granite dusts are not yet coated. So these are the free area where research can be done and promising results can be obtained. Now, what is this thermal spray coatings? Thermal spray coatings means if you want to coat any material on any other material, then you have to first melt it and make it accelerate in a particular direction to get deposited on the target surface. So that melting can be done either by gas combustion process or by arc processes. If it is a gas combustion process, accordingly you call it oxyfuel or detonation gone spraying or high velocity oxyfuel spraying. If it is to the arc process, then you can call it electric arc spraying or plasma arc spraying, depending on the source. Now, the process fundamentals are shown here. You can see there is a powder feedstock which is to be coated. Then powder particle melting will take place because of absorption of heat. The heat source can be plasma, heat source can be a flame, heat source can be combustion of gas, heat source can be a detonation or explosion. So depending on the heat source, the thermal spray coating process is named after the heat source. So plasma spray coating and high velocity oxyfuel coating, they are same thing. Only difference is that melting of the powder takes place in different ways, different heat source. So you can see this is the sequence of operation. The powder particle will melt, then it will be accelerated towards the target surface. This is the target surface, and then on the target surface they heat. When they heat the target surface, they form a splat. The splat in course of time gets cooled and solidifies. When it's solidified, it sticks to the wall and substrate surface, and consequent or subsequent deposition of such splats form a layer of coating. These are the process fundamentals. Now I'll show you some coated samples. So these are the coated samples. So substrate deposition and coated samples. So we have tried with the marble dust as the coating material. So these are the specimens prior to the coating. So this is mild steel, aluminum, inconel, and copper. Then the coating can be done. Feedstock material, the raw marble dust, and nickel chrome powder was added because sometimes the bonding is not proper with only marble dust. So some binder material is premixed, that is the NiCr, that is nickel chromium powder, and particle size ranging from 10 to 20 micron, and here the particle size are different. Now they are deposited in a lab where high velocity oxyfuel film is generated, and this high velocity oxyfuel frame is responsible for melting this marble dust and nickel chromium powder, and these molten particles are accelerated towards the target surface. And in the table below you can see these are the input parameters which are varied in that permissible ranges: the spray distance, powder feed rate, LPG gas feed rate, oxygen feed rate, air feed rate, etc. And accordingly the coating is made. The coating process, the beauty of coating process is that it is a very fast process, and very soon, in seconds or in minutes, the coating process is over, and a beautiful layer of hard coating can be obtained on a softer material. Now, for example, aluminum is a very soft material, whereas this marble dust and nickel chromium coating is a harder material, and they are deposited on this. So the surface becomes hard. So it is now in a position to resist any kind of frictional attacks or any kind of environmental attack where the chances of wear loss was prominent before. Now this is the SCM micrograph of raw marble dust, and these are the different elemental features. These are the coating surface after it is worn out. So different types of damage mechanisms are seen here. The diagrams are small, but there are crack formation, crack propagation. There is fracture, and there is also some plastic deformation due to sliding. So all these things are features. Of course, one who is going for a detailed research, all these features are very important to be identified. So what applications these thermal spraying samples can have? They can be used for reclamation or repairing or building up of the worn damaged surface. Undercoat for a paint. They can be used for electrical conductance. If it is a conducting material, they can be used for electrical conductance and for electrical insulation as well. They can be used for wear resistance, corrosion resistance, then heat resistance or heat resistance and heat insulation. Depending on what property you want from the material, you accordingly have to choose the coating material. And out of the industrial waste that are available, out of the construction waste that are available to us, and that list also is huge. So we have to analyze every waste and find out if it has got the requisite property or not. If it has the property, then we can select it. Maybe we can add an additive from the conventional domain and then make a composite using a technique which is thermal based. Can be a plasma, can be flame, can be oxy fuel spraying, can be an explosion, like that. The industries which use thermal spraying, the list is huge, and there is hardly any industry which do not use these thermal spray components. So you have aerospace, construction industries, electronics, hydraulics, oil, gas, pulp and paper. So the list is very long, as I told you. Aerospace industries, different types of aircraft is thermally coated. Now the turbine blades, very intricate component, but that intricate component can be coated with automated spraying system. This is the diagram of a automated plasma spray system, where you can see you can see the plasma flame, and then the coating is done here in the workpiece. This is the cross section of a the turbine, where the blades are visible, and the blades needs to be very delicately coated, because they are thick coatings. Thick coatings means, in the world of coating, any coating that is more than 50 micron are categorized as thick coating, or around 10-20 micron they are thin coatings. Automotive industries, again the list is very long. The exhaust pipes, turbocharger, piston and piston rods, cylinder liners, and the brake discs, they are all coated like this. Then automotive industry, these are different parts which are coated. Then in automotive industry you can see these parts, which are the crankshaft, the crank, the connecting rod. They are also thermally sprayed. And biomedical industry, you can see the artificial limbs. They are coated with hydroxyapatite HA material. HA material are biocompatible material, and they are the implants. Suppose someone's leg is broken, then one metallic element is placed inside the body. So they need to be biocompatible. They need to be compatible with the body element like flesh and blood. So accordingly, coatings are made. Then civil industries, any construction industries, in order to improve their functional life, coatings are essential. And without any surface treatment, there is hardly any component which is being used. Power plant industries, yes, power plant industries, coatings are used. This is the open view of a steam turbine, and here the turbines again are turbine blades, which are made up of very delicate material, need to be coated with delicate material. Again, of course, the industry waste cannot be used there, but exploration can be done. Agricultural implements, different agricultural implements are coated specially, and here the industrial waste coating are very much useful, because these are low end applications, and these particular teeth of all these equipments, they are coming in contact with the mud and slurry, the clay, mud and slurry. So they need to be friction resistant, and they need to be slurry resistant. So industrial waste like marble dust, granite dust, or red mud or fly ash coatings will be helpful for this kind of applications. Then conveyor belt rollers, this is another applications. Then power plant coal bends carrying pulverized coal. So these are some of the potential areas where coatings can be used. Coming to the last slide, I just want to tell the same thing which I've been telling repeatedly, that this is an area: use of industry waste, use of construction waste, use of biological waste, use of natural fibers in polymer composites, and in and sometimes these particulates in thermal spray coatings is a very promising area. So very less work has been done, although you will find a lot of literature on this. But if you go to a particular industry waste, you will not find more than 10 or 12 papers. So relatively much less work has been done in industry wastes, and even if it has been done, you can try with different matrices, you can try different techniques, you can hybridize it with another material. Two materials can be taken together and a new composite can be made. And you can add additives to make hybridized composites and hybridized coatings. And not only the wear characteristics is the only target characteristics, you can also target other characteristics such as electrical properties, dielectric properties, microelectronic properties, mechanical properties, damping properties, then acoustic properties, lot of things. There is no limit to the possibilities. And then modeling in simulation is another area which is very less explored, so that can be done. So with this, I complete my talk, and I hope in a short time I tried my best uh, to give you an impression of what can be done with industry and construction wastes. Thank you.
Thank you, sir, for this interesting session. Now the participants are can go for the interaction section, can interact with the speaker.
Participants, please ask any questions if you have. Yes, ma'am, you can ask.
Hello,
Yes.
sir. Sir, nowadays huge resource work is going on in coating area. Why
Hmm.
coating is so much important? Why coating is only used for to increase the lifespan? Only to increase the lifespan for different tools.
Coating is a part of surface engineering, science of surface engineering, and it in the later part of 20th century, the industry realized that 35% of the cost of the industry is going west because of lack of surface engineering. So actually you will find, if you see the history, 1975 70 1980 onwards, the coating industry has grown up. It is because of this the cost related significance to industries. So a lot of cost of the industry that it is giving as investment is going in overcoming the frictional losses and overcoming the environmental attacks. Environmental attacks include corrosion and erosion, and the
Yes, sir.
frictional cost includes the sliding wear losses and erosion wear losses. That is why the coating is done. Coating is done because, why coating is preferred? Why not other techniques like painting and other things? Painting is also a coating, but I'm
Yes,
talking
sir.
about why ceramic. Just a minute. Why ceramic coatings are preferred? Because the ceramic coatings, the adhesion strength of ceramic coating is comparatively higher than other what do you say, painting like galvanization or night riding.
Okay, sir. Thank you, sir.
Okay.
Good evening, sir.
Good evening.
Sir, when we work with this natural fibers, what are the things we should be careful about regarding the how should we prepare the sample? Uh,
Your question is, while working with natural fiber, what are the things we should be careful?
yes, yes,
Okay,
regarding the sample.
okay. So there are two things which are enemies of natural fiber. One is fire, one is water. Because they are hydrophilic in nature, they absorb a lot of water. Okay. So when they absorb a lot of water, what happens? Natural fiber composites, after composite is made, they dimensionally they what do you say, distortion takes place. So there is mechanical distortion. Another thing is that if the natural fiber composites are used in an area where the high temperature activity is going on, then they are it is not risk free to use them. So while working with natural fiber composite, if the natural fibers are treated, alkaline treated or acidic treatment is done according, depending on the chemistry, then at least the moisture absorption thing and the fire retardancy things can be reduced. Okay, that's why treated fibers are always preferred. There are other benefits of treatment, but these two are the main.
Okay, sir. Thank you. Thank you.
Hello. Good evening, sir. Actually, I am Dipankar Ghosh. I want to know how
Yes.
chicken feathers are used as a composite and where it is used.
Yeah, chicken feathers are, I mean, where it is used I cannot tell, but I mean where it is being used now, that I cannot tell. But chicken feather composites have been prepared, and chicken feather has got a peculiar characteristics. If you look at the chicken feather or chicken quill is the main branch, main stem on which the branches are made. So if you take it, view it under microscope, you will find there are a lot of pores. So it is, whole thing is porous. When the whole thing is porous, what happens? Air is trapped inside, and air is a bad conductor of heat and electricity. So chicken feather, when the feathers are used as a reinforcement in polymer, then that polymer composite is going to become a very good thermal insulator and a very good heat insulator. Sorry, very good thermal insulator and very good electrical insulator. So because it has got a thermal insulation potential is very high. So poultry feather composites can be used in auditorium, in theaters and in soundproof chambers, where they are acoustically insulative and thermally insulative. Okay.
Got
You
it,
can,
sir.
you can
Thank you.
find papers. You can find papers, chicken feather composites. We have published few papers on that. Chicken feather and also fish scale.
Yes, sir. Got it, sir. Thank you.
The participants. Sir, wait for a better.
Still not audible. Actually, I'm not able to hear anything.
Sir, in EPD coating method, is this waste? Can we utilize this waste powder, industrial waste, in PEO
Which
coating?
one? Which one?
In PEO coating with the electrophoretic deposition process.
Acha, electrophoretic deposition. No,
Plus,
I have no idea. I have no idea. But this can be explored with the thermal spray people. It is not a thermal spray. It is actually coming under plating, I think.
yes, anodization, plasma electric oxidation, the improved version of anodization.
No, if you are talking about plasma spraying, then it is very much suitable for plasma spraying. But if you are telling about electrophoretic deposition, it is not a thermal spray technique. It is a plating technique, it seems.
Dielectric breakdown.
Yeah, there was a question on chicken feather composite. What is that question? It's not visible to me.
Using
Yes. Yes. Yeah, I requested you to just type the question because
Sir, can you suggest any articles related to the chicken fibers composite?
yes. Once again.
Can you suggest any articles are available related to the chicken fibers with composite polymer composite material?
Yes. You can see chicken feather based, poultry feather based composite by Dr. S.C. Misra in polymer composite. The journal is polymer composite.
Sir, can you text in this spelling in the author's name?
Yeah, you can say Misra and Naik. Misra and Naik are the authors, and exact paper name I do not know, but it is polymer feather, poultry feather based composite, and the journal is polymer composite. And there is also another article in JRPC, Journal of Reinforced Plastic and Composite.
And one more thing, sir.
Yes.
Any plant waste can use this some seat covers or like some other product. Can
Very
you
good.
suggest?
Okay.
Any?
Very good question.
Okay, thank you.
If you see it in any Maruti vehicle,
Yeah.
the dashboard is made up of dashboard, no? The front side of the driver, front
Yes.
desk of the driver
Yes,
is made up of sisal fiber reinforced nylon. Sisal fiber. Sisal
Can you-
fiber is a plant based. Sisal, SISAL. SISAL. So there is a lot of research going on sisal fiber polymer composite, and that is automobile part. That is a direct example of where natural fiber is used in automobiles.
Okay. Thank you. Excuse me, sir. Can I get the contact mail ID to further this related to this feathers composite material?
Sure.
Can you
can-
send the mail ID in the chat box, sir?
Yeah.
Thank you.